Yeah, what I'll do is actually just go through a number of, I guess, case histories probably fairly briefly. So there won't be too much detailed geophysics for the geophysicists, and there won't be too much alteration for the geologists. So but what I'll do is just go through these. One of the reasons for copper gold porphyries is because there's a magnetite association with the gold. So the mineralisation of the potassic zone tends to retain the magnetite. So the Batu Hijau, Elang, Grasberg and Alumbrera have very nice mag anomalies. You can have late alteration destroying magnetite, and that happens at Golpu and Onto. And then we'll have a look sort of higher up in the system in the, I guess, lithocap, where you get the high sulfidation epithermal deposits. One thing I've had to go at total resource estimates for a lot of these things, and some are a bit rubbery, so don't quote me, but it does show you how big some of these systems are. A location, most of them are actually sitting in Indonesia and New Guinea, but I put this up so you can actually see Yanacocha is a high sulfidation deposit in Peru. Alumbrera is in northwest Argentina and a porphyry deposit there. And we'll just zoom into the box there, closer into here. Martabe is in North Sumatra, high sulfidation deposit. There are three deposits we're talking about on Sumbawa, Batu Hijau, Elang and Onto, and then Grasberg and Golpu. So I'll go pretty much through the order I had them before. Well, we'll get to that later, but really look at the response of the potassic zone, and then Onto and Golpu, and then go through the epithermal deposits. A very simplified version of alteration. You have a large magma chamber, and I guess as it solidifies, you're hoping the residual melt is actually enriched in copper and gold, and will come through as a porphyry, as a bunch of porphyry phases. There's a lot of sulfur in these systems, but there's also fluorine and chlorine, so they come through, interact with groundwater forming acid, and so you get very, very large, I guess, advanced argillic acid, or very advanced argillic alteration, also known as high sulfidation alteration, and can lead to the development of lithocap. So these acid fluids can go along a permeable horizon. They can be very extensive, and they can be a bit troubling when you're trying to explore under them. They're mostly, there's a lot of residual quartz plus clay, so they can be very extensive. And anyway, just zooming in now to just your porphyry stocks. This is one of the original porphyry models with Lowell and Gilbert on the left. So you have a potassic zone which hosts your copper and gold. Outside that, a phyllic zone and a propylitic zone. The phyllic zone, well, they call it a pyrite shell, I guess. There's a lot of pyrite in there, plus 10% pyrite. So you have, I guess, bornite chalcopyrite grading out through to pyrite, but that pyrite shell can produce very intense chargeability anomalies. And so if you're drilling a high chargeability anomaly in isolation in one of these systems, there's a very good chance you'll just get pyrite. There's that on the right's probably a slightly more modern model, and it shows the sulfide species. So you got in the centre. You can't really see that. Anyway, in the centre you have your potassic zone with bornite chalcopyrite grading out through chalcopyrite pyrite, and you get a lot of pyrite as a halo to these systems, and above in the altered zone on top of porphyries. And just to show where these systems fit, basically Elang, Batu Hijau, Grasberg and Alumbrera are actually sitting down in the potassic zone. Onto and Golpu have been overprinted by advanced argillic alteration, at least the tops of the porphyries have, and then you're getting up into the lithocap environment, looking at quartz and vuggy quartz in Martabe and Yanacocha that can host gold. we'll start with Batu Hijau and Elang. So just zooming in on Sumbawa, that's a pretty active island. The Tambora volcano up the top there is one of the largest eruptions in modern history in 1815 and led to the year without a summer in 1816. So it had a big effect on the world's climate. So it's fairly active. Batu Hijau and Elang are sitting down in southwest Sumbawa. Onto we'll get to later. So jumping to Batu Hijau, it's a large porphyry. You can see it's relatively before mining is the top left, and 2007 it's expanded dramatically since then, but that's when I took the photo. It's 900 million tonnes at 0.4, 0.5. Again, mineralisation associated with magnetic potassic zone, and I'll show you the IP. So basically, the geology is a series of tonalite intrusions. It's a pretty weak pointer. Sitting in here, intruding volcanics. Alteration down below, the light green's the potassic zone, the host of mineralisation, that grades are propylitic. The sulfide distribution, bornite, chalcopyrite, and chalcopyrite through to pyrite. So 1-to-1 with the potassic zone is the mineralisation, and the mag anomaly here is also 1-to-1 with mineralisation. This mag anomaly off to the south here is just magnetite in the propylitic zone and not of much interest. The magnetics on the left there, really gold, copper, and magnetic susceptibility are 1-to-1. And you can model up that magnetic anomaly with just a simple body with magnetic susceptibility shown there in the section, and it matches reasonably well. I guess the image up the top shows the magnetites actually occurs as veins and disseminations in the higher grade zones. Looking at the sulfide species, you have the chalcopyrite bornite zone through there, but you can see the pyrite as a halo to the mineralisation, so quite extensive pyrite around the edges and also at depth. The top right, gradient rate chargeability, there actually is a response due to that chalcopyrite bornite zone in the centre, but you can see the halo. I actually cheated a bit because the chargeability actually stays strong for a lot further out than this, but that makes a good story. And they did do 1 or 2 lines of dipole-dipole, so that's an inversion of one of the lines of dipole-dipole in the east-west section going across. And you can see in the centre here is where the mineralisation is, plus the black lines are showing sulphur. So you can see the pyrite shell actually sitting out here and at depth. Jumping now to Elang, again, it's pretty rugged. This is from the top left is from a helicopter sort of hovering above Elang. It's actually looking west back towards Batu Hijau, and you can see just above the clouds there is the volcano in Bali. So it's pretty rugged country. It's all helicopter supported drilling. It's getting bigger all the time. When I was there, it wasn't half that size, but now it's about 2.5 billion tonnes to make about 26 million ounces and 8.1 million tonnes of copper. It's not high grade, I guess. When we're looking at it, you're looking at about 0.3, 0.4 grams per tonne gold and % copper. It was discovered actually, as was Batu Hijau, by following up Bleg geochemistry. And again, the mineralisation is associated with the potassic zone. Just looking at the overall area, there is I think that's died, a sort of north-northeast trend of alteration. At Elang itself, it's a series of tonalite intrusions. Ladam and Cebu are actually epithermal veins. Gabung and Sepcat don't quite make it. They're still alteration, still porphyry centres, but the big ones at Elang. So the light green here at Elang is what was exposed in the creek, and so that's potassic alteration exposed. This dark pink is actually a lithocap. So most of that resource is actually sitting under the lithocap. And if you look at the magnetics, there's a a very nice discrete magnetic anomaly associated with that. On the northern side, it sort of splits into two with a better survey. On the northern side is what's exposed in the creek, and the main part of the anomaly is actually sitting under this lift cap. And just zooming in, so you can see a series of tonalites. I guess here in Batu Hijau, the early tonalites are actually the most mineralised, and then it goes through to the younger ones, the least mineralised, and the hole into this actually went straight into a vertical hole drilled early on, straight into the latest tonalite. So it was actually very weakly mineralised, and so it actually put off exploration here for about 10 years before they came back and found this, I guess, massive resource in these other areas. The magnetics, you can invert it, and it's 1-to-1. This is potassic alteration, this light green. It's really 1-to-1 with the magnetic susceptibility inversion. So it's a 3D inversion of the magnetics, and these isosurfaces are taken from that inversion, and pretty much the whole deposit sits within these isosurfaces. So it matches really well, except occasionally up the top here, there's late alteration destroying magnetite. So you can still get some mineralization up here, but generally the magnetics has been very useful in stepping out the drilling. It's covered with IP, and you can see here chargeability is actually quite complex. This is the 0.3, I think it's the 0.3 copper shell is in blue here and yellow over here. So you can see there's very high chargeability, sort of greater than 50 milliseconds in red. So these are really, really high. And there's quite a few high chargeabilities here that are actually where you'd only get pyrite and you do when they're drilled. There's quite a bit of information in here, but it's not chargeability doesn't necessarily give you a target, but it does show you the extent of the system. So everything here that's light green or above is highly anomalous. And there's a late intrusion in here that you can map as well with the chargeability. Resistivity is sort of quite interesting. The whole area is actually very conductive, the whole system, basically due to clay pyrite and sulfide veining. So the whole lot is actually reasonably conductive, and that's a bit of a theme for these calc-alkaline systems. And for anyone who might be vaguely interested in geochemistry, basically this is the mag anomaly. Moly works really well. Even above the lithocap, there's the soils. Zinc is fairly typical. It's sort of zinc depleted with a halo, and it matches 1-to-1 with the resistivity taken from the 3D inversion of the from the resistivity from the IP. Gold's interesting in that the gold is sitting down here that's elevated to the southeast, and you do get some of the epithermal veins here. And I guess it's a possibility that this whole block here has been downthrown, and you still get gold higher up in the system. And copper's a bit sporadic, but I guess the main thing here is you don't need to do geochemistry if you do IP. Anyway, jumping over to the east in New Guinea. Grasberg's here in West Papua, and you can see it's just absolutely massive. One of the biggest copper and gold deposits in the world, absolutely massive. It's a pretty well endowed part of the world, and the other one we'll talk about is Wafi-Golpu, sitting over here, sort of northwest of Port Moresby. But you can see here, it's very well endowed. There's Bougainville sitting over here, Lahire, and then a number of other deposits, Octeta, Porphyry, sitting through there. Looking at Grasberg, extreme topography. So basically, the pit here sits at about 4,000 metres. There's a glacier up here at about 4,800 metres. It's very difficult to get rid of your waste and things, and it's just extreme. And getting to work, you actually go about 2 kilometres vertically. This is the last bit, which is 800-metre vertical cable car, which is quite interesting. But yeah, it's massive, sort of 2.5 billion tonnes at over a gram copper and a gram copper, a percent copper and a gram gold. Half of that is in skarns. So about 1 billion tonnes in the porphyry. Greater than 7% is about 10% magnetite. There, it's highly magnetic. Well, judging by the topography, no one's actually done any ground electrical surveys. But I have done, I have measured samples. The thing is, if you get a sample with a chalcopyrite ray, it's going to be conductive as anything. So it's not necessarily definitive. I'll show you the mag inversion. But basically, again, it's a series of porphyry intrusions intruding this breccia zone here, and it's hosted in carbonates. So it's very well confined, which may be why it's so rich. And you can actually see the outline of the red up here. Well, you'll have to make it out yourself. There's the 1 ppm gold shell and the blue 1% copper. Well, that's green's 1% copper. So we're well confined and a very impressive anomaly deposit. You can model up the magnetics. So it's about a 2000 nanotesla mag anomaly in a very non-magnetic host in the carbonates. So it stands out very well. And even the fixed wing at altitude, it stands out very well. And that can be modelled with a 600-metre diameter pipe-like body that matches it quite well. But to actually match the curve properly, you do need to have this lower underlying intrusion here, which you don't actually. I mean, there are underlying batholiths to all of these things, but it's not often you actually can measure them or see them. And this is just one of the samples I measured, and not surprisingly, it's extremely conductive. But when you're actually standing in the pit, these veins are quite extensive, and I'd expect the whole mineralised system here to be highly conductive. But I don't have the survey to show that. Jumping now back to Argentina, we're all over the place. Alumbrera is it's smaller, not quite 500,000 tonnes at 0.6, 0.5. But it has a very nice absolute type case magnetic signature. So you can see here it's almost so I guess again it's a series of porphyry intrusions, intruding volcanics. The alteration here is type case sort of potassic to phyllic to propylitic, 1-to-1 with the mag potassic zone in the centre, magnetite destruction around that in the phyllic zone, and then background volcanics. This is one of the few porphyries I've seen with a potassium anomaly, and I think that's just because it's a hill in the middle of this valley here. Generally, I guess the potassium alteration minerals in porphyries, I don't think they weather well, and you don't necessarily see a good potassium response with porphyries. Quite different with epithermals. Epithermals stand out very well in the potassium response. This is from a very old resistivity survey, an airborne resistivity survey. So the whole thing is actually quite conductive, and they have done a bit of IP here, and you can see that. So the whole system here is reasonably conductive, and it's a topographic, I guess, basin. It affects the topography. So something else you can look for in a porphyry system. So jumping now to deposits that have been overprinted, the Wafi deposit, again, it's a very large deposit, 26 million ounces, 8.8 million tonnes of copper, and most of that's in the Golpu porphyry. There are contributions here from the Wafi-Golpu sulfidation system and the Mbonga porphyry. So there are a few porphyries here. It's a very big system. And you can see the topography there in the outline. Just regionally, you're in it's hosted in the Owen Stanley metamorphics. You can see the location. If you can make it out anyway, Golpu, Wafi and Mbonga. And it's associated with this Wafi transfer zone. What's interesting is you can have a look, the outline of Golpu here on the right is in red, and there's no sign of a mag anomaly. So I guess actually most alterations associated with these porphyry systems are magnetite destructive. The potassic's the exception, but and when you get out to the propylitic, you may preserve some magnetite. But So it's quite low magnetically. Nambonga is a great mag anomaly, and that's was found by drilling that mag anomaly. Kesiago down south is actually it's a porphyry, but most of it's been sheared off by by faulting. So most of it's been lost. And the reason you don't get a mag anomaly, the alteration, so you have this advanced argillic alteration going down to about 500 metres. You have a lithocap on top, quartz alunite, plus various clay zones, bits and pieces. What's interesting here is the copper extends, the magnetite, you don't have a mag anomaly because it's completely destroyed down to 500 metres, but the copper continues up towards the surface. So the copper hasn't been depleted with that alteration. We'll get back to that anyway, but basically an IP survey was done by CRA quite a long time ago, and they didn't get out of the system at all. So anything there that's green or above is highly chargeable. So that's, when you're getting up to hundreds, it's just ridiculous amount of pyrite. So you're not outside the system at all. The only thing that's not anomalous in here are some of these blue zones. So you're really not getting out of the system. Resistivity-wise, you are mapping the lithocap quite well. So this is a 100-metre depth slice below topography of the 3D inversion. So it's mapping the lithocap. What else is interesting here too is these blue zones are still less than 100 ohm metres. So you're not outside the system, but the whole thing is still reasonably conductive. And this is a slide. I used to say that that's Kim Frankham there, but apparently he took the photo. So anyway, he time domain EM's not done a lot in this sort of topography because logistically it's not. I mean, IP you can go along a cut line. Time domain EM, especially moving loop like this, you have to have cross lines as well. So it's a difficult logistical thing to do. So it's not done very much. This is one of the few places that has been done. And a 3D inversion of that EM, you can actually see the lithocap kicking in here at the 100-metre below topography slice. You're starting to see some conductors coming in at 200, and it really maps the Golpu system really well at 300. So you are seeing a very good conductor within a conductive system. Jumping now to airborne EM, exploration wasn't consulted when they flew this, so that was done for development purposes. So that's why the funny shapes, and they did along roads and all sorts of things. But basically here you are seeing the extent of the system as a conductive zone here. You're seeing the lithocap quite well above Golpu. So this conductive zone here is mapping the extent of the system. These are just conductive sediments out to the west. But airborne EM can be a very good way of mapping a system. So this is just going a bit deeper. The other one was 100-metre depth slice. This one's going a bit deeper. So it doesn't quite, I mean, you can see Golpu in here, but it's not one-to-one. I don't think you'd go and drill that, but you really can see what's happening with the system. And as you go deeper, I mean, I guess the thing is that the reason you have that conductive zone up is sort of secondary copper minerals, so chalcocite, carbonate, it's just secondary copper sulfides, and I think they probably grade down to chalcopyrite, bornite at depth. So at depth, you're getting these sorts of chalcopyrite veins. So I think the whole of the porphyry mineralisation is going to be quite conductive. And just to summarise that, so you can see the copper here again. Resistivity, I have that being very conductive with a lithocap. Magnetic susceptibility is quite well. It kicks in deep, but it's too deep to be seen from the air, from the surface. Gold's a bit sporadic. Sulfur, there's a lot of sulfates, so it's not quite all pyrite. So it's a combination of sulfides and sulfates. Chargeability, I think, extends much further than this. So I just copied the sulfur. But anyway, I think the interesting thing here is that you can have these highly conductive zones, something else to look for when you don't have mag anomaly. Anyway, jumping now to Onto, which is absolutely massive. 35 million ounces of gold, 18 million tons of copper. It's one of the biggest copper deposits in the world. Sitting in over here in southeast Sumbawa. The thing about it is there's a very broad zone of alteration here. There's about a 5 kilometre by 9 kilometre lithocap, which if you can make out here, the location of Onto itself projected to the surface in red. That yellow dot there was a porphyry discovery that was found by drilling a mag anomaly with some geochem. We'll get to that. So that was found first, and I think without that they wouldn't have persevered to find Onto. Looking at the mag, so that's the porphyries, this Hompalau East porphyry, HLE, and the Onto outline is sitting in here with, there's a bit of mag fuss here. A lot of this subdued magnetics is due to the lithocap. So lithocaps, they don't necessarily go through. They're usually just a blanket, so they can just subdue your magnetics. But anyway, Onto was actually drilled by stepping out. I guess there are geochemical responses here in pretty much the last hole here. They did use the mag plus some very small outcrop of breccia with some mineralised clasts in it. So that was about the last gasp, and they hit a pretty amazing deposit. There's a very good actually YouTube video by Burrows on the discovery of Onto. It's probably worth a look. Anyway, looking at what they found, it's just a series of porphyries. So these are, I guess, when you're looking at Batu Hijau or even Elang, you're looking at, Batu Hijau is probably the porphyry centres or the mineralised zones, probably about 400 metres in diameter. This one here, the porphyries themselves are, like 1 kilometre by 2 kilometres. So there's a lot of porphyry alteration. These have intruded this breccia system, the porphyries. So there's a breccia system first, and then I think these relatively unaltered andesites came in then, and the porphyries then intruded. And you can see the outline of the, I think that's the 0.2 copper shell in the blue here. The other interesting thing here is that the deepest holes, well, this one here is just over 2 kilometres and still in mineralisation and still in altered porphyries. We'll just have a look at the alteration now. Basically, these andesites at the top are relatively unaltered, and then you get into all of this high sulfidation, all the typical stuff, fuggy silica to silica to all the clays and various things. So it's altered very deeply. Advanced argillic is at least 1.5 kilometres, and then you get into regular alteration that just continues. So they're never out of alteration. So there's no magnetite left in these things. And so an MT survey was done covering this area. So these are just the MT stations. MT just measures resistivity, really, for the non-geophysicist or even for the geophysicist. So an MT survey is done in here, and so you can see the outline of Onto HLE here, and that's the survey. There was an original survey done with the black lights. They're about 400 by 800 metre spacing. And this is a 3D inversion of the MT, looking at depth slices as you go down. So what you have here is when you look at the more near surface at 200 metres, these things are highly conductive, and they're actually active hydrothermal systems. So it's very hot water, and they're quite conductive. So you're looking for a conductor in a very high conductive zone. When you get down to 500 metres, you're starting to see the top of Onto. So it's a screaming conductor in a very conductive zone. And as you go down, it's just 1-to-1. It's just a spectacular MT anomaly. And the reason for it, I guess covalite's a copper sulfide. 1 Siemens per metre is pretty conductive. This is up for 1 million Siemens per metre. It's covalite, and it's I guess it's not solid covalite, but it basically 15% sulfides, covalite and pyrite. So it's just that's the reason for the conductivity. The other thing is the pore fluids here are going to be quite hot and possibly acid and saline. So there's very good connectivity in the whole system. So it's extremely conductive. And just looking at a section, this is a section actually through the MT. So the MT 3D model, and you can see here the hydrothermal systems. Onto, well, it's not drilled. Yeah, it only goes down 2 kilometres, so it continues. But whether this continues or not, it seems to go forever. But it's actually quite difficult to constrain this to not keep going. So whether when you get into porphyries the sulfides continue or not, I don't know. But anyway, it's not closed. Anyway, jumping now to something probably a little smaller, looking at the high sulfidation systems probably in the lithocap. So this is just some alteration of the done by Antonio Rebus a while back. You don't have to worry about any of this sort of stuff on the left. The main thing here is you've got vuggy silica and quartz alunite sitting in clay. So basically these things are incredibly conductive, thousands of ohm meters within clay, which are tens of ohm meters. So you've got a very big contrast with these things. And jumping now to Martabe, the other thing too is because you are in silica bodies, these things can seriously affect the topography. So Martabe, that whole ridge there is a high sulfidation system. That's probably all been mined now. You can just make out some of the old Normandy drill pads built here with bamboo. They thought it was dipping the other way, but they didn't need to, but it's just crazy. All of this was actually covered with IP, and I told them not to do anything dangerous, but they didn't miss a station. So I don't know how they did that. They did slow up at times, and I did ask them, but anyway, it's not a big deposit, but in the other scheme of things, but still, 5.8 million ounces at 1.4, and just looking, we covered it with IP resistivity. Basically, that's the hill you're looking at, highly resistive, 1-to-1 with gold, and actually the gold could be improved on to fat match some resistivity. Alteration's fairly simple, just high silica and clay. The geology is really complicated because there's just breccia system on breccia system. So there's so many phases of breccia, it's actually really, really quite messy. So it's much easier just to look at the alteration and the resistivity. And this is just a depth slice. Basically, these are 1 gram gold contours on the depth slice of resistivity 50 meters below surface. That's the hill you were just looking at. And it's really 1-to-1 with the resistivity. Gold is on the right. So, and in fact, I think they would have liked the resistivity to use in their resource model. And it can be flown from the air. So this was the anomaly you just saw. These also are all high sulfidation deposits, various ones. I have no idea. It's been a long time since I worked in here, so I'm not sure which ones have been mined out or not now. But you can see from the air, it's actually picking these up reasonably well. There's a granite over to the east, and there's low sulfidation epithermal veins here, but there's not a lot of false positives if you look at the whole survey. So it does a pretty good job just with airborne EM. And I guess the big high sulfidation deposits are Yanacocha in Peru. So this is getting up for 50 million ounces in Peru. Again, the gold is hosted by resistive silica bodies. And there's been any number of surveys. This was an IP survey, the resistivity from an IP survey. This anomaly in here is actually found by resistivity. It's sort of 200 meters down, but still oxidized, so still it's still economic. But well, despite how that looks, resistivity is 1-to-1 with these silica bodies, and it works really well. And anyway, just to conclude, really magnetics, I think it doesn't have to be porphyries. I think most exploration does pretty well with the best mag you can get for a number of reasons. But as far as porphyries go, you can get a direct target. from these gold-rich porphyries if the magnetite's preserved. It's probably better, actually. One good thing, if you do have a mag anomaly that's conductive or chargeable, that's even better, because you can get late intrusions. It also picks up magnetite destruction, so you need a pretty reasonable survey to pick up magnetite destruction. Resistivity, I guess the whole system stands out pretty well as a conductive zone, these calc-alkaline porphyries anyway. And there is a possibility of very high conductivity within these with secondary copper or chalcopyrite veining. The high sulfidation deposits are highly resistive silica bodies, so you're looking for high resistivity in that case. There's extensive pyrite, so it's good for actually seeing whether you've got a porphyry system or not. You do expect a lot of pyrite. I guess everything I'm saying, there are some exceptions. So how much pyrite you get can depend on your host. If you don't have iron in your host, you don't get a lot. But basically, they're high sulfide systems, so you do expect a lot of pyrite. Gravity, I haven't actually shown any gravity, but the stuff I've seen, really, it's just so complicated with all the alteration and topography that I don't think it's cost effective in these sort of areas anyway. But it can be useful if you're actually looking for that underlying magma chamber. Radiometrics, you get that with mag, and it can be really useful for mapping geology, and it's surprising how well it works through the jungle. That actually works really well at times. Lithocaps are generally low, so they're sort of dark zones in your radiometrics, but you can, it's worth though looking for alteration, particularly with the epithermal veins. And topography is one of the few things that we have worldwide in pretty good topography. It's always worth looking at. So you can have anything from high sulfidation silica bodies forming these massive ridges and cliffs right through to landslides and things caused by alteration. So that's something else you can look at. But anyway, that's a very quick rundown of porphyries. Thanks.